Okay, so the last week, last 4 lectures, so 9, 10, 11, 12, we've been talking about forces and acceleration, so Newton's second law. And we're now going to switch a little bit and kind of look at Newton's second law again, but from a slightly different perspective. So here we have what will end up being the thing you've got to think about when you do all of these problems. There we go. There we go. There we go. That is, a force does work only if that force is moving in the same direction as the force is acting. So for example, if I carry a box and walk across this floor, I'm doing no work. But if I carry that same box and walk to the second, up to the top of the lecture hall, I am doing work. And defining that becomes part of how we sort of separate out problems. So we have done sum of forces equals mass times acceleration. I might as well keep it the same color. Sum of forces equals mass v dv dx is going to be this week. And sum of forces equals m dv dt is the last week before reading week. So what we'll end up doing is ending up looking at a set of equations that kind of look like this. Sum of forces equals mass times, say, for a system, acceleration, T1 plus work, 1 to 2 equals T2, and mv1 plus T1 to T2 of f dt equals mv2. And we'll look at it in terms of angular momentum too. But the important thing here is that for these two, this week, or last week and next week, we have vector terms. But here, we're going to be looking at scalar terms. And so things become a little bit easier to sort of deal with intuitively. Oops, I think I skipped something. I didn't want to skip it in that order. So if I have a force that's operating on some sort of particle and it moves along some path. So the blue line is a path, ft is the tangential component, normal is the normal component of force acting down towards the center of curvature. And in the process of looking at this, let's blow that up a little bit. I can write this as work done on a path that is going to be f ds cos of theta. So I can do it 2 different ways. The way I tend to write it is f cos theta ds, but that's because it's a component of force that's acting along the path. I can also write it as the component of the path that's acting along the force. Both of those mean basically the same thing. They come up with the same result, but honestly, in terms of thinking of the physics of things, it's often easier to say it's f cos theta ds as opposed to f ds cos theta. Now, if force or work is just force times the distance, I can integrate over the entire path. So I can integrate this and sort of say, well, integrating from point 1 to point 2 along the path, say 1 over here, 2 over here. I can say that the work done is just the integral of 1 to 2 of du and the integral of the component of force acting along that path. And I end up with u1 to 2 is equal to f cos theta s2 minus s1. So I have a component of force, it's all acting along there, it's sort of doing things and it's sort of working pretty well. Is there a question? Go ahead. Yeah?
What exactly are U and T?
Where's T?
The one that
Okay, so force tangential. So you're used to mt coordinates at this point.
it was in the previous slide, capital T.
Where's the previous part?
There.
Oh, sorry. Thank you. This will eventually be, I'm going to define that today. Kinetic energy and work. And this is force ds. And this will eventually be 1/2 mass times the velocity squared of this, of this particle. So the particle is going to be moving with some velocity. We haven't gotten there yet, but that's sort of where I'm going to define things. Go ahead.
Are we going to be dealing with this when you integrate, you took the force cos theta out of the integral, but if it's a function of,
Say it's traveling and it's sort of moving up and down, it's changing, theta is changing with time, then you would have a different term.
do we deal with that?
We deal with it slightly differently. I would probably put it as a force of x, force of y, and give you an expression for it. So it's not always going to be a direct sort of relationship. It's probably something I should have. Really kind of maybe coming back to this. Just to sort of separate out the 3 weeks, or the 10 lectures that we have. The first one is really instantaneous, so we're looking at forces and accelerations. The second one are going to be force, velocity, and the distance problem. This is how we're going to deal with this. That's why you have work that you look at. The last thing that you're going to deal with is force, velocity, and time, which is next week, and that's momentum. And so when you deal with momentum, you should be able to separate out each of those to the type of problem you're being asked for. So let's go look at something a little bit more complex in terms of its motion. We have something that is traveling again on a path, but how do I describe things in, say, my x, y, z coordinates? So work 1 to 2 is equal to, say, a1 to a2 of f dotted with dr if I want to go all vector on it. And I can just write that as s1 to s2 of f cos of alpha ds, which equals, again, s1 to s2 of ft ds. You are not going to solve problems like this. You're going to look at it from the perspective of what component of force is acting along the path, and you will end up with an integral that looks as A1 to A2 of fx dx plus fy dy, and very infrequently, but f z dz. So all you're looking for is the displacement of a force along the coordinate direction of interest. So in order for work to happen, you have to break it up into its component parts. So the work is just the area under the curve. You're just integrating. So straight definition of integrals. And let me see if I can. Oh, I had double copied it. So let's look at something like this. I have a particle and the weight is acting downwards. I'm not worried about how it's moving. I'm just worried about what happens at the beginning and the end of the path. So it starts here, it ends up there, or it goes the other way. Either way, it doesn't matter. So du is equal to fx dx plus fy dy, integral from position 1 to position 2. Let's just call that 1 to 2, and this is h. du equals u1 to 2. The integral from 1 to 2 equals fx dx plus integral 1 to 2 of fy dy. Well, going from 1 to 2, it's moved from position 1 to position 2. So if we agree that it sort of has moved vertically, there's a difference. So y1, y2 is different. x1 and x2, on the other hand, it's the same sort of location, or it's a different x in terms of x1 to x2, but the force that's acting on there, the weight, is acting normal to that path. So if you do the dot product, if you take the cos of that, in both of those cases you end up with 0. So this term goes to 0. So if you're going to write it, you can say work 1 to 2 is equal to the integral of minus mg dy and ug 1 to 2 is equal to minus mg y2 minus y1, which equals minus mgh. So the work of gravity is like, we deal with it a lot like we do with springs, with spring force. Weight is acting downwards, the path is going upwards, and so they are acting diametrically opposed to each other, and so it becomes a negative value. So work 1 to 2 is minus mgh. So if I go from top to bottom, or bottom to top, just 2 seconds. Bottom to top, I'm going a positive h, and I'll do negative work. If I'm going top to bottom, I'm going positive h, I'm going negative h in that case, in which case I'll have a positive work. Go ahead.
I still don't understand why fx dx goes to 0.
Because there's, what component of force are we looking at that's acting in the x direction? I haven't put a force in the x direction. And so g, if I take the cos of that, is going to be 0 in the x direction. So in order for work to be done, it has to be something like this, where you have a component in x and y, or a component in x. So traditionally, you may have a case, say, for example, I'm pushing a box across the floor, then I'll do work against friction.
Okay, so this time you're just like moving it up.
I'm just moving it up. It doesn't matter how the path is taken. I can walk all the way around there and end up the top, or I can walk all the way over there, and in fact, all of the work that I've done on the box is going to be just the same. It's just a change in height. And this becomes one of the important aspects of work. And it's also one of the reasons why I hate work, because I prefer to go with something called conservative forces. And so the later part of this lecture, I'll actually flip the sign on that term. It'll still be the same. Oops. But I'm going to use a different way of referring to it.
But like, why does it go like this?
Oh, because I can. So if I had done this or this, it's the same work.
That's just as a result of you moving this.
That's it. That's the whole thing. So it doesn't matter any path if this is the same h. Is still the same no matter how I get there. The only force acting and the work done is the one of the weight. Go ahead.
Is it safe to assume that he'll move uniformly in the x direction and there's no acceleration of force?
There's nothing, unless you're told otherwise. Don't assume anything is happening unless you're told otherwise. Okay? All right. As you can see at the bottom, or just below here, have a spring. Force of a spring, we already know, is just force. And I didn't use delta here. Force of the spring times delta x, or k times delta x. It's negative because the force of the spring opposes the displacement. So if I stretch it and cause a positive displacement, I'll have a negative force. If I compress it, I'll have a positive force and a negative displacement. So in these cases, I have to work with what I have there. I'm going to have force of the spring is minus k delta x. If I use work, I can write that as u 1 to 2 is equal to the integral 1 to 2 of minus k dx, and put in all the terms. 1 to 2 equals 1 to 2. No. I want to solve it. So if I do the integral, do x1 to x2, position 1, position 2, I'll end up with work 1 to 2 is minus 1/2 k x2 squared minus x1 squared. Now I really don't want to leave it as a minus and a minus here anyways, so I'll just flip these signs around. So it becomes 1/2 k x1 squared minus x2 squared. And again, there are different ways of approaching it. This is work. If we start to look at conservative forces, I think they make a little bit more sense intuitively. Questions?
Where do we get the 1/2 squared?
Integration. Yeah, which I should have said kx, right? So you have kx integrated 1/2 kx squared. You have 1/2 kx1 squared minus x2 squared. Now the top one is going to be pretty obvious. If I have a frictionless surface, the force of friction is 0, and if I push a box across that force or surface, it's going to do no work because there is no force. However, this will get a bit more important in chapter 6. And that is when I have rolling without slip. And rolling without slip means that this object comes into contact with the ground and it has an instantaneous zero velocity. So this is one of the first instances you see in this course, well, it's the first instance in this course, where an object has size. So it can rotate, and as it rotates, it's in contact with the ground, and because it's in contact with the ground and there's no slip, v equals 0 at that point. So if it can't displace, it can't do work. Oh, good. I gave you everything at once. So forces that do no work is a reaction at a frictionless pin supporting a rotating body. So say, for example, something like this. Ooh. That is, the red spot is a pin. That bar is some sort of link, and it's rotating about that. Reaction where I had a frictionless surface, the one at the top. Reaction of a roller moving along its track, not so important, but we will talk about that later. Weight of a body when its center of gravity moves horizontally. So the very first thing we started with was the case of a body that sort of translates, and if you look at the top, it doesn't matter what the path that I take is, as long as I end up at the same point. So my work is going to be the same whether I do this, or if I go out to Starbucks, get a drink, come back, and walk up there. So all of that is to tell you that this is a really interesting tool for analysis because it doesn't depend on what's happening to your body. It matters what happens at the beginning and end. So where we kind of end up then is that we start to look at Newton's second law again, and we make the substitution that force is equal to mass times acceleration. And we end up with acceleration is equal to v dv ds in this chapter. So this is where the analysis sort of follows through. And no. So I can write that directly as 1 to 2 of f of t ds equals m v dv from v1 to v2. So if I have a force that I am acting on in some way, so for example, if I'm running around with a weight and I want to know what's happening or if that weight has changed, I can integrate from position 1 to position 2 and write a better v. And look at my initial velocity, initial speed really, and my final, and calculate my final speed. So this first term is just work. This second term is more interesting, because now I have something in terms of velocity squared. So I have mass, velocity squared, and this 1/2 that comes out of the integral. So if I do work 1 to 2, it's equal to T1, or T2, excuse me, minus T1. And T equals 1/2 mv squared. So that's my kinetic energy. So now I have an expression that tells me the difference in kinetic energy is equal to the change in work, or the work done during this motion. So T1 plus work, 1 to 2, is equal to T2. And that ends up being sort of a primary one, but combined conservative So the problem with this is that it's going to combine conservative and non-conservative forces, and I will define those a little bit in a little bit more detail a bit later in this lecture. But a conservative force is one that if I, for example, if I walk up to the top and I come back down, I will have a change in gravitational potential of 0. If I stretch my idealized springs and I allow it to return to its original position, compress it, and let it stretch back out, in all of those cases, it will return to the same energy level. So those conservative forces often are easier to deal with, not as work, but as something else, like a potential energy. So when you're dealing with work and potential energy, they have dimensions of mL squared over T squared. And in US customary units, energy is foot-pounds, and in SI units, they're joules. Now, curiously enough, if you look at what a joule is a Newton meter, which is the same units that we use for moments. So this becomes a bit problematic, and you really have to think about what the problem is you're dealing with. But foot-pound in US customary and Newton meters for moments. And we've started talking about those. As engineers, you kind of care at how you're doing work. So the rate of doing work is actually an important quantity. We don't really cover it in the course. We don't do very much with it. I do introduce it because I think it's an important definition for you to have. And if you look at power, it's the rate of doing work. And if you take the definition of work, you can say it's F dotted with dr dt over dt. You can say, oh, I can rewrite that as F dotted with dr dt. Dr dt is just velocity. So force times the velocity gives you the amount of power that you're using. again, when you look at power, it really matters how you're getting it out. So for example, if you input 1,000 kilowatts and you get 1 watt out, you're not very efficient. And so efficiency is also an important measure of what you actually are doing and how effective it's actually, or how effective it is. And it's a useful sort of secondary thing. So what you get over what you pay for. It's an eta. So it's a n with a curly bit on the end. So, as you probably know, you've looked at the text. They split the text up into 2 parts, or 2 chapters on this in this section. One to deal with individual particles and one to deal with systems. Well, systems end up being pretty much the same thing. So a system of particles with a bunch of internal forces and external forces acting in there, you can say that the total kinetic energy, I equals 1 to n for n particles, is 1/2 mi vi 1 squared plus total work done on each of the particles it's a crazy formula to say very little. So the initial kinetic energy of all particles work done by external forces work done by internal forces final kinetic energy of the system. So if I sum over all particles that I have, I can say they have an initial kinetic energy. I perform work on those particles, and in the process of performing work, I have to separate them between the internal and the external forces, and then I get the final kinetic energy. And it's kind of important to differentiate just a tiny bit here. In most cases, I can get rid of the internal forces. And I will show an example, and I'll kind of put the starting point of that example next. But sometimes, if you have relative motion between 2 particles, then you can have internal force work. And here's a case of exactly that. And this is one we kind of did last time when I was looking at the forces and the acceleration of two particles. The work is going to be described as Fi. I'm going to try, hold on, dri plus ij, sorry, dri plus fji dr j, which equals fij dotted with dri minus drj, which equals fij dotted with dri relative to j. And I wanted to do all of that by including that these are all vectors. All right. So, if I look at the internal forces, I can say that Fij dotted with dri plus Fji dotted with drj, if there are equal, opposite, collinear, and no motion between the two, that would go to 0 normally. In order for it to go to 0, the relative displacement between both of those terms has to be 0. So dri minus drj is really I relative to j. So I can rewrite it in that form and just keep that in the back of your head. I will do that example right there in a little bit more detail. But for now, I kind of want to stop on that. But I just want to point out that internal forces can do work, unlike internal forces in terms of second law analysis, which we did in the previous part of this problem, or the previous version of this problem. I do not like dealing with work. And so what I try to do is cover in this lecture everything so that I end up back at the first point, and I can say that there is a potential energy at each of those points. So mgy1, mgy2 all depend on a location. And I can write at position 1 and position 2. And I can say that V1 equals mgh1. And the important thing here, if I were careful, is to define h1 and h2. And if I can do that, I can write mgh2. And the idea is that a conservative force is, again, one force that could go, you can go up, you can go back down, and the delta in that energy is 0. And it has the same units. It's going to have joules. I can do the same thing with springs, and it's just going to be k delta x squared, or x1 squared and x2 squared, if everything is relative to, say, the unstretched length. And what that does is allow me to write a new equation, or a slightly modified conservation equation, T1 plus V1 plus work 1 to 2 equals T2 plus V2. So I can write everything now as positive numbers, which I find more helpful to me as I'm trying to keep track of things. So positive 1/2 mv1 squared, positive mgh1, positive 1/2 kx1 squared. Work 1 to 2 then becomes non-conservative forces. Which is generally friction. And I deal with friction by just doing the integral F delta x, the displacement along the path, force of friction times its displacement, and it's just, again, a straightforward sort of number that I'll get out of this. These two are the final values at the end. So it's the beginning and the end, and everything sort of works out a lot easier because I can understand. For me, it's a lot easier. Both of these expressions are the same. The only difference is this form of the equation combines these two things, or three things. And if you rewrite everything, so if I take the gravitational potential energy at V1 and V2, and I could say that, example, T1 plus 1/2 mg, or not, mgh1 plus work 1 to 2 equals 1, or T2 plus 1, man, I want to put on a 1/2, mgh2, I end up with T1 plus mgh1 minus h2 plus work 1 to 2 equals T2. So in essence, it's this, it should be, and it must be, the same expression over here. So both of them still work out the same way. So you can do it both ways. Either way is fine. I just find making sure that you take into account everything that's going on, it's a lot easier with that upper approach. T1 plus V1 plus U1 to 2. And the only thing you worry about is the non-conservative terms that are going to appear. Go ahead.
Yeah, I'm just confused about the 1/2 kx squared.
Yeah. That's the spring work, or the spring energy. So spring potential energy for me in that expression, and it can be rewritten the same way as spring kinetic, or spring work. Yeah. So last week what we did was this problem. And this problem was a pain in the neck, because when I had to solve it, I had to remember a whole bunch of things. I had to solve for forces, I had to solve for accelerations, I had to calculate velocities from that, and in 5 minutes I'm going to solve this. And I don't really care about the tension in the cable. That's not straight. That's not interesting. But again, for those of you who may not remember, there's a kid in a swing. The kid has a mass of 27 kilos. You treat the kid as a particle as usual. Find the speed when theta is equal to 90. Kid starts from rest at theta equals 60 degrees. So position 1, position 2, and I'm going to define a datum from the top. And I'm going to use that kind of notation, this upside down triangle with a couple lines underneath it, to indicate my 0. So in this case, h1 is equal to minus length of the swing times sine of 60. So it is a distance below the datum. So h1, I'm going to spend a lot more time on this than you'll ever do when you solve it on your own. At 90 degrees, the kid has reached the bottom of the swing, and because the kid's at the bottom of the swing, it's just the length of that chord. So the length of the swing. Now again, the kid is below my datum. And so the way I've defined my datum, I have set it so that that's a negative length of the swing, which is negative 3 meters. Okay, it's not working. So if I look at that term, I have gravitational potential energy. I have kinetic energy at the beginning, gravitational potential energy at the end, and kinetic energy at the end. Okay. Which is just mg h1 minus h2 There we go. This goes to 0 because the kid starts at rest. Don't know why. Yeah, all right. The masses disappear because they don't play. They're on both sides. V2 squared's there. I got a half. I got to sort of do some numbers, and I get V equals 2.81 meters per second at the end. And if you solve through for it or look at the old solution, it's the same thing as before. Now, if I had written this as a work term, I would have written T1 plus work 1 to 2 equals T2 1/2 mv1 squared plus mg h1 minus h2 equals 1/2 mv2 squared, which is the exact same relationship that I have. So they're both the same. So the first term on the left is going to go away. And that goes to 0. So if that term goes to 0, I have exactly what I wrote just above. But again, you're going to have to decide how you solve these problems. But really, I think it's easier just to visualize things here